Hello everybody, welcome back to our mini-series on measurement-based quantum computation. This is the second and final part of the universality proof. So here you see again the outline of this lecture. So universality is first, then comes fault tolerance, and then come two other pieces. Here, for this lecture, we have just one item on the menu, and we are continuing from the previous lecture, and today we are talking about the universality proof. This is the recap of the structure of the proof. The first three steps, which we did last time, established the elementary components, so the gates we have to implement. The first was wire, just the identity gate, needs to be done somehow, but then the more useful gates, the 1-qubit rotations and the entangling gates, like the CNOT. Today, in the second part of the proof, we will be combining these pieces. So today everything will be about composition. So in step 4, we talk about how MBQC gate simulations combine. And in step 5, we will talk again about how the qubits that are measured in the eigenbasis of sigma z don't matter. And then finally, we will have to talk about the impact of the randomness of the measurement outcomes. So these are the 3 steps ahead. Okay, first step for today is step 4 overall. We are talking about composition. So what we want to show is that the MBQC gate simulations compose in exactly the same way as the gates compose by concatenation. So that's just another commutation game like what we have played before. So let's do it one more time. Okay, here you see 2 consecutive gates being executed. So as we saw in part 2, I think this was, every elementary gate here comprises 2 measurements. One implements a Z rotation, one implements an X rotation, and now we have 2 of them. 4 logical measurements in total. And so you see on the left side of the circuit, you have the preparation of the cluster state with input, and then come the 4 measurements. So now we will reorder commuting operations. And this is what you'll see here. So the measurements of the first 2 qubits have been moved to an earlier time, and the entangling gates among qubits 3, 4, and 5, the lower ones, have been moved to a later time. Yeah. Okay, and so now you just kind of regroup these operations and find that you have this upper left block. This is one of the gate simulations, and you have the lower right block, and it's the other gate simulation. So the gate simulation of the 2 gates combined equals the succession of 2 gate simulations. So that proves composition. Step number 5, we want to show that the cluster qubits measured in the eigenbasis of sigma z are redundant. We want to show that they don't have a logical effect. So let's do this here only in the simplest possible instance. And once you follow this example, then you can do the more general ones by yourself. So what we want to show here is the following. You have a 3-qubit cluster state. You measure 1, namely the lower qubit of the 3, in the eigenbasis of sigma z, and that effectively removes that cluster qubit, and you remain with a 2-qubit cluster state. Okay, that's another commutation game. So let's look at it. So what you see here is a cluster state first prepared. So this is the local X preparations plus subsequent conditional phase gate mimicking the Ising interaction. So that's the first thing that happens, preparation of the cluster state. And then we have the measurement of the last qubit in the eigenbasis of sigma z. And so for simplicity, we have the outcome 0 here. Okay, so the first step in this commutation game is to propagate that projection on state 0 to before the conditional phase gate. That can be done because the two gates commute. And what we now have on the left of the circuit is the preparation of plus followed by a projection onto the state 0. That does nothing but prepare the state 0. And next, we look at this combination between the state 0 and the subsequent conditional phase gate. Well, if one of the qubits involved is in the state 0, the conditional phase gate doesn't really do anything, and so the conditional phase gate can be removed without loss. And when we now look at the situation, well, what we have remaining is a 2-qubit cluster state and an unentangled qubit in an eigenstate of sigma z. All right, so this pretty much shows it. I just want to make one little remark here. So we have done this only for measurement outcome 0. But what if the measurement outcome is 1? So you may repeat the analysis. It is not much different. It's a tiny little difference. The measurement outcome matters, but in the end, you do get a tensor product between a local state and a cluster-like state. Step 6, the effect of the randomness of the measurement outcomes. Okay, so let's have a look at this picture. It is pretty busy. So what you see here is the following. You see a sequence of 5 cluster qubits in a row being measured. And on top of that, you have the corresponding circuit when you translate this measurement sequence into a quantum circuit. So that equivalent circuit, more or less, about the difference we talk in a moment, begins with the preparation of a plus state. Then you have a bunch of rotations, alternating, rotations about the z-axis, rotation about the x-axis, z again, x again, so on and so forth. And then finally an x measurement. At least that's what you want to have. But now you have this tiny complication due to the randomness of the measurement outcome. So as we discussed in step 2, what you get in addition are these byproduct operators. So the first gate, which is about the z-axis, is supplemented by a byproduct operator sigma z that is either there or not there, depending on what the measurement outcome of qubit 1 is. And then on the second qubit, you have a byproduct operator sigma x, because it is associated with the rotation about the x-axis. And again, it is there or not there, depending on what the outcome of measurement 2 is. And then qubit 3, 4, 5 are just the same in this regard. Okay, I want to emphasize one more point. This is important not to forget. And it's also going back to step 2. And what I want to say here is that the angle defining the measurement basis, you see this in the formula here on the screen, and the angle of the logical rotation that is being implemented are related. They are related in a very simple fashion, namely they are the same. But to that sameness, there's a tiny correction. There's going to be, the sign may be flipped. And that is the effect that we are going to talk about. But for now, remember, the choice of the measurement basis determines the angle of the logical rotations that we are implementing. Okay, so we have these random byproduct operators here. So that's the complication that measurement brings, and we may have them there, may not have them there, but we are sure that we don't want them. So we want to get rid of them. And overall, the strategy of getting rid of them is propagate them past all the gates and past the final measurements. Because what happens after the final measurement cannot have any effect on the computation. That's the overall idea. But this forward propagation in time is not so easy, so entirely easy, because these byproducts do not commute with the logical gates that we propagate them through. And this effect we now need to study. All right, so let's just watch how one particular byproduct, namely a byproduct caused by the measurement of the second qubit, propagates. So let's assume the outcome of the second qubit was 1. So we have this byproduct operator sigma x sitting there in this place as it is indicated. Okay, first propagation step. We propagated one step forward in time. And so what we see now is that the Pauli operator sigma x that is being propagated forward anti-commutes with the Pauli operator sigma z that generates the rotation. And so the effect of the forward propagation is flipping the rotation angle into minus itself. That's all that happens in this step, but it's a significant change. We'll come back to this. So in the second step of propagation, nothing happens because the Pauli byproduct, sigma x, commutes with the rotation. And then comes the third step. So it's like the first. The rotation is about the z-axis, the byproduct is in x, we have anti-commutation, and therefore in the forward propagation, the rotation angle is flipped. Okay, so now we still need to propagate that byproduct past the final readout. Here in this case, the byproduct and the final measurement commute, so there is no change. And then finally, as we said earlier, we observe that everything that happens after the readout measurement we can just forget about. And so we just throw it out. And if we now collect what has happened, we find that the rotation angles have been flipped, namely on qubit 3 and on qubit 5. So let's look at the interaction between qubit 2 and qubit 3. Yeah, so what we will find here is that the measurement angle phi m and the rotation angle phi of the logical rotation, they are now related in this still rather simple fashion. Namely, the rotation angle of the logical rotation equals the measurement angle times the sign factor plus minus 1, or more specifically, minus 1 to the power of the measurement outcome occurring on qubit number 2. Yeah, they are the same up to this sign factor. Okay, so if you read this relation in this way, it looks like the outcome of the measurement at site 2 determines the rotation angle. But that's of course not how we want it. We don't want the rotation angle implemented on site number 3 to be random. So what we do now is that we move the sign factor to the other side of this equation. So this is an equivalence transformation. And now, well, we can read the same equation as follows. So now the measurement angle on site number 3 is determined by the rotation angle that I want and the outcome at site number 2. Okay, so this was pretty much the argument. So let's summarize. What we have found so far is that the measurement outcome of site number 2 determines the measurement basis at site number 3. And to make this possible, qubit number 2 must be measured before qubit number 3 can. And that is basically the relation that we have the two. So to summarize, the upshot is that the randomness of measurement outcomes determines temporal order of measurement, and measurement bases need to be adjusted according to measurement outcomes obtained before. Okay, and this completes the universality proof. So what we would basically be done, but I want to make 2 more remarks. So this is what I already said. So, but it is kind of an important point to make here. So the randomness of measurement determines the temporal order in measurement-based quantum computation. And now you may wonder, so is this order any different than the circuit model temporal order? And yes, it is. And let me tell you why this is so. So what you see here in the middle is the general situation. We have a measurement basis in the XY equator of the Bloch sphere, and the effect of earlier measurements is to flip it. So the basis can be this or it can be this, but that's really all that's happening, this flip back and forth. So that's the general situation. So now there are two special bases that do not change under this flipping. And this is the X basis, clearly nothing changes at all. And the other is the Y basis. And in the Y basis there is a little bit of change, namely the eigenstates are interchanged, but the basis as a whole remains the same. So therefore nothing in these special cases, X basis and Y basis, nothing needs to be adjusted according to prior measurements. And so these measurement bases drop out of temporal order. So now let's have a look and see what kind of gates can be implemented with X and Y measurements. Okay, and here you see them. These are the Clifford gates. All the Clifford gates can be MBQC implemented with X and Y measurements only. And so those gates, no matter where they occur on the circuit, they just totally drop out of temporal order. So that's a marked difference in the temporal order in measurement-based quantum computation. Just wanted to point that out. Okay, so this is pretty much the end of this lecture. Just want to show you what's coming up. So next time we will discuss fault tolerance. And here, if you want, you have a reading list covering the subject that we have so far discussed.